For most of human history, we believed the universe was calm, predictable, stable, and eternal. Stars shimmered in the sky, unmoving across a lifetime. The heavens looked like a serene dome stretching forever. Everything above our heads seemed fixed, reliable, and unchanging. That illusion survived for thousands of years, and even when telescopes arrived, even when science began peeling back the layers of the cosmos, the same quiet assumption remained. The universe might be big, yes, but it was steady. It behaved. It did not do anything dramatic. It did not change its mind. It simply existed. And then, in the 20th century, humanity stumbled upon a discovery so shocking, so disorienting, so unbelievable, that it shattered our most basic understanding of reality. We learned that the universe is expanding, not gently, not slowly, but relentlessly, restlessly, with a force so overwhelming that space itself stretches like an invisible fabric pulled from every direction. We learned that galaxies are not sitting still. They are rushing away from each other. The universe is swelling, growing, transforming. And that was only the beginning, because the real shock arrived later, when scientists realized that the expansion of the universe is not slowing down, as one would expect from gravity pulling everything inward. Instead, the expansion is speeding up, accelerating, racing outward with increasing ferocity. That moment, when astronomers saw distant supernovae glowing fainter than they should, marked one of the greatest scientific shocks of all time. It was as if the universe whispered, "You do not understand me." And indeed, we did not. Because nothing in our physics predicted this behavior. Nothing in our intuition made sense of it. Nothing in our centuries of star-watching prepared us for the revelation that the cosmos is stretching faster and faster with every passing moment. Imagine standing on a vast plain, watching distant mountains. Every hour the mountains drift farther, but instead of slowing, they accelerate. They dash away at speeds you cannot comprehend, as if pushed by an invisible hand. That is our universe. Except the mountains are galaxies, and the invisible hand is something we still cannot explain. This invisible hand is what we now call dark energy, a name that reveals nothing except our ignorance. A placeholder for a force that rewrites the story of cosmic evolution, a force so powerful that it overwhelms gravity on the largest scales, a force that has already shaped the fate of the universe and will continue shaping it long after every star you know has burned out. But to understand how mind-bending this discovery truly is, you must step into the moment when humanity first glimpsed it. The year was 1998. Two teams of astronomers studied distant exploding stars, ancient light traveling across the depths of cosmic time. These exploding stars, Type 1 supernovae, are cosmic lighthouses. Predictable, consistent. Their brightness acts like a ruler for measuring distance. By observing them, astronomers could map how fast galaxies were moving away. Everyone expected the same result. The universe should be slowing down. Gravity should be pulling everything together. Expansion should be weakening. But reality refused to obey. Those distant supernovae were too dim, too faint, too far away. They were not where they were supposed to be, and the only explanation was unthinkable. The universe was expanding faster today than in the past. The expansion was accelerating. Space was stretching with increasing speed. The universe was not winding down. It was ramping up. Like a roller coaster we hadn't realized was climbing an invisible slope. This discovery overturned everything, because for the expansion to accelerate, something had to be pushing it. A repulsive force, a cosmic pressure with no known source, something built into the fabric of space itself. As far as we can tell, dark energy behaves like a property of the vacuum. Empty space possesses energy. And when space expands, more empty space appears, which means more dark energy appears, which means expansion speeds up even more. It is a cosmic feedback loop, a runaway process that could continue indefinitely. The more the universe grows, the more it wants to grow. This is not only mind-bending, it is disturbing. It implies that the fate of the cosmos is not a gentle cooling, but a relentless tearing apart of every structure not held together by gravity. Over unimaginable stretches of time, galaxy clusters will drift away until they become islands in a sea of blackness. Eventually, only our local group of galaxies will remain visible. Beyond that, the rest of the universe will slip past the cosmic horizon, moving away faster than any light can reach us. Future civilizations, billions of years from now, will look at their night sky and see almost nothing. They will have no evidence the universe ever contained millions of galaxies. They will believe they are alone in a small, static cosmos, a tragically incomplete picture. The accelerating universe erases the evidence of its own vastness, but the expansion itself is not the only mind-bending part. What makes this discovery so shocking is that we have no idea what dark energy actually is. We know it exists. We know it drives cosmic acceleration. We know it makes up the majority of the universe's total energy. But we do not know its nature. It might be a constant energy inherent to space. It might be a dynamic field that changes over time. It might be an illusion produced by a misunderstanding of gravity. It might even be the result of interactions with other universes in the multiverse, unseen dimensions tugging on ours. The truth is, dark energy might be telling us that the universe is far larger and stranger than our equations can grasp. And here is the irony that makes this discovery even more breathtaking. Einstein predicted something like dark energy, then abandoned it. When he first developed the equations of general relativity, he realized that a universe filled with matter should collapse or expand, not remain static. So he added a term to counterbalance gravity, the cosmological constant, a repulsive factor, a push. When Hubble later discovered the universe was expanding, Einstein removed this term, calling it his greatest blunder. And then, decades later, the universe forced us to resurrect it. Perhaps Einstein's greatest blunder was actually his greatest insight, but one he could not recognize at the time. Yet the accelerating universe creates deeper mysteries. If dark energy is constant, expansion will continue growing forever. If it strengthens over time, the universe could undergo a catastrophic future, the so-called Big Rip, where galaxies, solar systems, planets, and even atoms are torn apart. If dark energy weakens, the universe might slow its expansion or even collapse. In other models, the universe oscillates between expansions and contractions. The truth is, cosmic acceleration does not simply tell us about the present. It asks us to confront the future of everything that exists. And here is where the mind truly begins to bend. The accelerating universe suggests that we occupy a very special moment in cosmic history, a moment when galaxies are still visible, a moment when the cosmic microwave background still illuminates the sky, a moment when the universe is old enough to be rich in stars, but young enough that its structures are not yet lost to expansion. This era will not last. We are living in a privileged window, a cosmic golden age of visibility. This raises uncomfortable questions. Why now? Why are we alive at this peculiar moment when dark energy has only recently begun dominating, yet the universe remains observable? Is it coincidence? Anthropic selection? Evidence of deeper laws we do not understand? Some physicists argue that this timing hints at the multiverse, that there are countless universes with different amounts of dark energy, but life can only arise in those where structures form before being torn apart. In universes where dark energy is stronger, galaxies never form. In universes where it is weaker, early collapse prevents life. This idea means our existence is not an accident. It is a consequence of cosmic selection. But no matter which explanation one prefers, the accelerating universe forces us to confront an idea that is hard to believe. Reality is not built for stability. It is built for transformation. Space is not static. Space evolves. The universe is not calm. It is restless. It is a living process driven by forces we barely understand. What makes this discovery especially mind-bending is that it is not ancient history. It is happening right now, at this very moment, in every corner of the cosmos. Galaxies are drifting, light is stretching, space is swelling, the universe is changing even as you read this sentence. Every passing moment increases the distance between galaxies. not because they move, but because space grows between them. The expansion is not something the universe once did. It is something it is doing, continuously, endlessly, inevitably. And there is something hauntingly beautiful about that. Because the accelerating universe reminds us that nothing is permanent. Everything changes, everything evolves, even the cosmos itself. The universe does not grow old by fading into stillness. It grows old by expanding into immensity. We once believed the universe was a simple stage on which matter played its role. Now we know the stage itself moves. It shifts beneath the actors. It stretches. It warps. It transforms. Space is not a container. It is a participant. The accelerating universe forces us to see reality in a new way, not as a static thing, but as an unfolding story. This discovery marks one of the most profound moments in the history of human thought. Because once you learn that the universe is expanding faster with every moment, once you understand that the cosmos is driven by a force we cannot see, cannot touch, cannot explain, you can never look at the sky the same way again. The night sky becomes a time machine, a living map of an expanding mystery, a reminder that the universe is always more than it appears, a reminder that reality is deeper, stranger, and more magnificent than our minds can grasp. And this is only the first discovery. The cosmos contains secrets far more unbelievable than this one. For as long as astronomers have studied the heavens, one assumption guided their thinking more than any other. Everything you see in the universe is everything that exists. If you map the stars, the galaxies, the nebulae, the clusters, then you have mapped the cosmos. The visible universe was the universe. Light was our guide, our measurement, our cosmic truth-teller. But then something unsettling happened. As scientists attempted to understand how galaxies move, how stars orbit, how clusters hold themselves together, they encountered a contradiction so severe that it cracked the foundation of astronomy. The universe was behaving as if it contained more mass than the eye could ever detect. Galaxies spun too fast. Stars stayed bound when they should have flown off into darkness. Clusters held themselves together with a grip that visible matter simply could not explain. It was as if the universe were whispering that the majority of its substance was hidden. Not dim, not faint. Hidden, invisible, undetectable. A kind of matter that interacts with gravity but remains completely absent from the world of light. This invisible stuff became known as dark matter, a name that conveys both mystery and frustration. Because we still do not know what it is, we see its fingerprints everywhere. We feel its gravitational pull. We can map its distribution across the cosmic web, but we cannot touch it, detect it directly, or identify its particles. It exists without revealing its nature. It is real without being visible. It shapes the universe while remaining beyond our reach. The story begins in the early 20th century when astronomer Fritz Zwicky studied the Coma Cluster, a vast collection of galaxies bound together by gravity. He expected the galaxies to move slowly around their shared center of mass. Instead, they raced with incredible velocity, moving so fast that the cluster should have torn apart long ago. The galaxies were like marbles being spun on a plate. Based on the visible matter, gravity was too weak to hold them together. Something was missing, something heavy, something enormous, something accounting for far more mass than the stars, gas, and dust combined. Zwicky called it Dunkel Materie, dark matter. Astronomers dismissed his conclusion for decades. They believed he miscalculated, but time would prove him right. In the 1970s, Vera Rubin studied spiral galaxies, expecting their stars to orbit like planets around the sun, faster near the center, slower at the edges. But that was not what she found. Instead, stars far from the center moved at nearly the same speed as stars close to the core. They were orbiting too fast, dangerously fast. Based purely on the visible matter, stars in the outer regions of galaxies should have been flung into intergalactic space. Yet they remained bound. Something massive, invisible, and everywhere was holding the galaxy together, something forming a halo around every galaxy, something that outweighed ordinary matter by several factors. It was a mind-bending moment. The universe had been hiding the majority of its mass in plain sight, and we had been blind to it. What makes this discovery even more unbelievable is that dark matter does not behave like anything we know. All familiar matter interacts with light. It absorbs, reflects, emits, or scatters photons, but dark matter is utterly indifferent to light. It passes through it. It passes through planets. It passes through stars. It passes through you. You are being crossed by dark matter particles right now, every second, without feeling a single one. It is like a shadow that carries weight, like a ghost that tugs on galaxies, like a presence defined only by the way it bends the paths of stars. But even this description fails to capture the strangeness, because dark matter is not just a hidden ingredient, it is the dominant ingredient. The majority of matter in the universe is dark matter. The atoms that make you, your planet, your body, your air, all of that is a minority, a cosmic afterthought. The universe is built mostly from something we cannot see. Visible matter is the exception, not the rule. This is not merely surprising, it is deeply unsettling. It suggests that the universe we experience with our senses is only a thin veil draped over a much larger, unseen structure. The cosmos we know is a ghost of the cosmos that truly exists. Light shows us only the surface of reality. Gravity reveals the deeper skeleton. But dark matter becomes even more unbelievable when you consider what it does. It creates structure. Without dark matter, galaxies would not exist. When the early universe cooled after the Big Bang, matter needed places to gather. But visible matter alone was too slow, too hot, too chaotic to collapse quickly enough. Dark matter, however, was cold, calm, and unaffected by radiation. It clumped first. It formed invisible halos, massive dense wells of gravity. Those halos became the scaffolding of galaxies. Gas fell into the dark matter wells, cooled, condensed, and eventually formed stars. In other words, dark matter made the universe possible. It shaped the cosmic web. It dictated where galaxies grew, how clusters formed, how structure unfolded across billions of years. The visible universe rides on the framework of the invisible one. Dark matter is not an accessory. It is the architect. Yet even with all these clues, dark matter refuses to reveal itself. Physicists have proposed countless candidates: weakly interacting massive particles, sterile neutrinos, axions, supersymmetric particles, hidden sector particles, dark photons. Every possibility sounds stranger than the last, but no experiment, not one, has confirmed any candidate. Detectors buried deep underground, shielded from cosmic radiation. Detectors in mountains, detectors in old mine shafts, detectors with liquid xenon, detectors with cryogenic crystals, decades of searching and still nothing. If dark matter is made of particles, they are unlike anything we have ever encountered. But there is another possibility, one that bends the mind even further. Perhaps dark matter is not matter at all. Perhaps it is a sign that our understanding of gravity is wrong. Maybe gravity does not behave the way we think on large scales. Maybe the equations that describe planets and stars break down when applied to galaxies or clusters. Modified gravity theories propose that dark matter is not a particle, but an illusion, a misinterpretation. The universe might not contain hidden mass, it might contain hidden rules. But these theories struggle to explain all the evidence, because dark matter does more than alter galaxy rotations. It also influences gravitational lensing, the bending of light around massive objects. It affects the cosmic microwave background. It shapes the distribution of galaxies. Its fingerprints are everywhere, consistent, unavoidable, undeniable. If dark matter is not real, then countless independent observations are all wrong in exactly the same way. It is far more likely that dark matter truly exists, and we simply do not understand it. And that mystery becomes even stranger when we consider galactic collisions. When the Bullet Cluster was observed, it provided one of the clearest proofs of dark matter's reality. Two galaxy clusters collided at immense speeds. The visible gas crashed together, heated up, and slowed down. But the mass distribution, measured through gravitational lensing, did not slow down. It passed straight through. The mass of the system was not in the visible gas. It was in something invisible that moved through the collision untouched. Dark matter did not collide, did not heat, did not interact. It simply glided through as if the visible universe were irrelevant. This was a cosmic X-ray, revealing the skeleton beneath the flesh. But perhaps the most unbelievable aspect of dark matter is how unbothered it is by us. It does not interact with atoms. It does not form planets. It does not ignite into stars. It does not bond or react or combine. It does not make chemistry. It does not make life. It is the dominant form of matter in the universe, yet it is utterly alien to everything we know as matter. Imagine a parallel form of reality, overlapping ours, shaping it, influencing it, pulling on it, yet forever invisible, forever unreachable. That is dark matter, a shadow universe intertwined with our own. And here is where things become even more extraordinary. Dark matter may not be one thing. It may be many things, multiple types of particles, entire families of interactions, a dark sector with its own physics, its own forces, even its own complicated behavior. We may be living inside a two-layered universe, the ordinary matter world we see, and a vast dark world we do not, interacting only through gravity. The cosmos may contain two universes superimposed on each other, one bright, one hidden. But regardless of its nature, one thing is certain. Dark matter is a mystery with weight. It is not metaphorical, it is real. It holds galaxies together, it shapes the universe, it dictates the movement of stars, it anchors cosmic structure. Without it, there would be no Milky Way, no solar system, no Earth, no life. The most unbelievable part is that everything you see in the night sky, every star, every planet, every glowing nebula, is only a trace, a faint decoration on top of a massive invisible infrastructure. The illuminated universe is just the tip of a cosmic iceberg. And we are only beginning to understand how deep that iceberg goes. For centuries, humanity believed black holes were simply monsters of the cosmos, terrifying, destructive, inescapable pits of darkness waiting to swallow anything that ventured too close. They were imagined as cosmic vacuums, devourers of stars, tearers of space, and destroyers of worlds. The idea of a place where gravity becomes so overwhelming that not even light can escape felt like pure science fiction when it was first proposed. But as the decades passed, as equations sharpened and telescopes deepened, something extraordinary happened. Black holes went from myth to mathematical oddity to observational certainty. And then, just when we thought we understood them, they changed again. Black holes are not merely holes. They are engines, tunnels, forges, factories, gateways, the most mind-bending regions of space-time ever discovered. And the more we uncover about them, the stranger they become. A black hole begins as a star's death cry, the final collapse of a massive body that is burned through its nuclear fuel. When such a star can no longer support itself, gravity takes over. The core collapses, density skyrockets, atoms shatter, electrons are forced into protons, and even those are crushed into something deeper. Eventually, the collapse becomes unstoppable, squeezing matter into a point so dense that our physics breaks. This point becomes the singularity, wrapped in a boundary known as the event horizon, the ultimate one-way door of the universe. But calling it a point is misleading. The singularity is not something we understand. It is not a physical object. It is a problem in our equations, a place where general relativity admits defeat, a place where quantum mechanics must take over, yet quantum gravity remains elusive. But the region outside the singularity, the event horizon, is where the true magic happens. It is not a wall. It is a transition, a threshold of no return. Once you cross it, escape becomes impossible, not because you are pulled inward, but because the fabric of space-time itself now flows inward faster than any attempt to flee. It is as if space becomes a waterfall, plunging toward the singularity with irresistible force. Even light, the fastest thing in the universe, cannot outrun the flow. But this is only the beginning of what makes black holes unbelievable. Because the structure of space-time near a black hole is not simply curved, it is twisted. Rotating black holes, known as Kerr black holes, drag space-time around them in a phenomenon called frame dragging. Imagine stirring honey with a spoon. The honey swirls, pulled along by the spoon's rotation. In the same way, a spinning black hole pulls the very fabric of space into a whirlpool. This creates an ergosphere, a region outside the event horizon where space-time is dragged so quickly that nothing can remain still. Within the ergosphere, you must rotate. Standing still becomes impossible because space-time itself is moving. This creates one of the most mind-bending possibilities in physics, energy extraction from a black hole. The Penrose process allows an object to enter the ergosphere, split into two parts, and one piece escapes with more energy than it entered with, energy stolen from the black hole's rotation. Black holes, in other words, can be tapped like cosmic batteries. This alone is extraordinary. But what makes black holes even more unbelievable is that they are far from empty. Their surroundings are some of the brightest objects in the universe. When matter spirals toward a black hole, it forms an accretion disk, a swirling, superheated ring of plasma. Temperatures reach millions of degrees, magnetic fields twist and snap, particles collide with unimaginable force, and the violence of this process creates beams of energy, relativistic jets, that blast into space at nearly the speed of light. These jets can stretch for hundreds of thousands of light years, bright enough to outshine entire galaxies. This means black holes are not silent destroyers. They are cosmic engines capable of releasing more power than any other known phenomenon. Some galaxies are powered by supermassive black holes that feed only occasionally. When they do, they ignite the galaxy's core into a quasar, a beacon visible across the observable universe. But the strangeness does not end there. Black holes also evaporate. Stephen Hawking revealed that quantum effects near the event horizon cause black holes to emit radiation. Over unimaginable stretches of time, they lose mass. They shrink, they fade, they vanish. A black hole, the symbol of ultimate confinement, becomes the symbol of impermanence. Even these titans of gravity eventually die. And yet, the most shocking aspect of black holes is not their power. It is what they imply about space, time, information, and the nature of reality. One of the greatest puzzles in physics is the black hole information paradox. If you throw matter into a black hole, all its information seems lost forever. But quantum mechanics states that information cannot be destroyed. So where does it go? Does it remain stored on the event horizon like a hologram? Does it escape through Hawking radiation? Does the interior of a black hole connect to another region of the universe, allowing information to reappear elsewhere? Or is our understanding of quantum mechanics incomplete? This paradox is not a small issue. It is one of the biggest clashes between general relativity and quantum physics, two theories that otherwise form the foundation of modern science. Black holes are where these theories collide. They are the laboratories of ultimate physics, the testing grounds for the deepest truths about reality. But the mind bends even further when we consider the possibility that black holes might be bridges. Einstein and Rosen proposed the idea of wormholes, tunnels in space-time that connect distant regions of the universe. These wormholes resemble the geometry of some black hole solutions. Could a black hole connect to a white hole on the other side, ejecting matter into a different region of the universe? Could black holes be portals to other dimensions? Could they be cosmic recycling machines, turning old matter into new universes? Some physicists even propose that our universe itself could have emerged from the interior of a black hole in a parent universe. That each black hole might ignite a new Big Bang on the other side. That universes reproduce through gravitational collapse. The multiverse might be a family tree, with black holes serving as seeds. This idea is wild, but it fits surprisingly well with certain cosmological models. It suggests that reality might be self-generating, self-replicating, and infinite. And for all their mystery, black holes are not rare. They are everywhere. Stellar black holes litter the galaxy. At the centers of galaxies lie supermassive black holes, millions or billions of times the mass of the Sun. They anchor galaxies, shaping their formation. Without black holes, galaxies would not exist as we know them. These behemoths regulate star formation, sculpt the cosmic web, and influence the fate of entire galactic systems. So here is the unbelievable truth. Black holes are not cosmic anomalies. They are cosmic architects. They do not simply exist. They organize, they regulate, they create. The universe is structured around them. The cosmic ecosystem depends on them. They are the beating hearts of galaxies. They are engines of creation disguised as engines of destruction. And there is still more. When two black holes collide, they produce gravitational waves, ripples in the fabric of space-time that undulate across the cosmos. We detected these waves for the first time in 2015, confirming a prediction Einstein made a century earlier. When those waves arrived on Earth, our planet stretched and squeezed by distances smaller than a proton. Not metaphorically, literally. The planet vibrated in response to two black holes merging billions of years ago. We felt the heartbeat of the universe. Think about that. Across the vastness of space, through unimaginable distances, the merger of two objects we cannot see sent a tremor through reality itself, and we detected it. Black holes do not just warp space. They broadcast messages through it. The more we learn, the more black holes resemble something between a phenomenon and a gateway. They blur the boundary between physics and philosophy. They force us to re-examine what space is, what time is, what information is, what matter is, what reality is. They are the cosmic mirrors in which our understanding of the universe breaks and reforms. And in the end, the most unbelievable truth of all is this: black holes are not black. They are luminous with meaning, glowing with mystery, radiant with knowledge. They are the brightest idea the universe has ever forced us to confront. If you could step outside the Milky Way and drift into the silent darkness between galaxies, you might expect to see emptiness, a void, a blank backdrop stretching across the cosmic sea. That is how we imagined the universe for centuries, islands of stars floating in darkness with nothing but distance between them. But this picture was always an illusion created by our limited senses. The farther we looked, the deeper we probed, the more the universe began to reveal something astonishing beneath its visible surface. Something vast, something hidden, something woven into the fabric of everything. What astronomers eventually discovered is that galaxies are not scattered randomly like grains of sand dropped on a black table. Instead, they are arranged along immense structures, threads, filaments, waves, bridges, and clusters, forming a vast skeleton that stretches across the cosmos like the framework of a colossal invisible creature. This structure is known as the cosmic web, and it is one of the most mind-bending discoveries ever made in the history of astronomy. The cosmic web is not just large. It is the largest structure ever observed, spanning hundreds of millions of light years. It is a network of filaments made of galaxies, dark matter, gas, and gravity itself. It is the unseen architecture that shapes everything we see. Even the Milky Way, with its hundreds of billions of stars, is just a bead on one of these filaments, a tiny spark clinging to a vast thread of matter that stretches across unimaginable distances. The cosmic web is the skeleton of the universe. But for most of human history, we never knew it existed. The story begins with the distribution of galaxies. When we first mapped them, we expected to find randomness. Instead, we saw patterns. Galaxies gathered in clusters, clusters gathered into superclusters, and those superclusters formed walls, massive sheets of galaxies thousands of times larger than anything we imagined. Between these walls lay immense voids, regions almost completely empty, like bubbles within the foam of a cosmic ocean. Something was guiding the arrangement of matter, arranging it into a tapestry. Those early maps hinted at a deeper structure, but technology had to advance before we could truly see it. As telescopes improved and surveys expanded, the cosmic web revealed itself in breathtaking detail. The Sloan Digital Sky Survey, one of the most ambitious mapping projects ever undertaken, charted millions of galaxies and created a three-dimensional view of the cosmos. What it showed did not resemble a random universe. It resembled a neural network, a cosmic brain. Filaments connecting clusters like synapses, nodes where matter accumulated like neurons, empty spaces between them like the voids of a living mind. The visual resemblance is so striking that some scientists jokingly call the cosmic web the cosmic brain. But it is more than a metaphor. It is a reflection of the deep patterns nature builds into every scale of existence. What makes the cosmic web so astonishing is that it was predicted long before we could see it. The early universe was nearly uniform, with only small fluctuations in density. These tiny variations, barely noticeable, were the seeds of structure. Where there was slightly more matter, gravity pulled more matter toward it. These areas grew denser. Where there was slightly less, matter drifted away, leaving empty regions. Over billions of years, these fluctuations grew into vast filaments of dark matter. Gas fell into the dark matter filaments, cooled, condensed, and eventually formed galaxies. The cosmic web formed not from chaos, but from microscopic differences amplified over cosmic time. Dark matter is the true architect of the cosmic web. Without it, matter would never have clumped into filaments. Visible matter is too slow, too hot, too reactive. It spreads out like mist instead of gathering like stone. But dark matter, cold and non-interacting, clumped efficiently. It formed invisible highways of gravity, and these invisible highways guided galaxies into their positions. The cosmic web is, in essence, a dark matter structure illuminated by the faint glow of galaxies. A skeleton of shadow revealed only through its gravitational pull. And yet the cosmic web is not static. It moves, it flows. Matter travels along its filaments like rivers of stars drifting toward cosmic basins. Galaxies slide along gravitational gradients, migrating over billions of years. Clusters grow at the intersection points, massive knots where filaments cross. These nodes are among the most extreme environments in the universe. They host the largest structures ever observed, including colossal superclusters that stretch across hundreds of millions of light years. One such colossal structure, the Hercules Corona Borealis Great Wall, is so mind-bendingly large that it challenges our understanding of cosmic uniformity. But even this is not the most unbelievable part. The cosmic web behaves like something alive. It grows, it evolves, it thickens over time in some regions and thins in others. Simulations show that the filaments vibrate and fluctuate, flexing like cosmic tendons. Clusters orbit slightly around the centers of gravity created by intersections. Gas flows along filaments, feeding galaxies like arteries feeding organs. The universe is not a static sculpture. It is a dynamic organism, changing slowly on timescales so immense that only simulations can reveal its motion. And those simulations reveal something haunting. The cosmic web connects everything. Every galaxy is part of a filament. Every filament is part of a wall. Every wall touches multiple voids. Every void is surrounded by structure. There is no isolation, no true emptiness. Even the darkest regions of space are shaped by the gravitational influence of the web, even if they lack light. The universe is not a collection of islands. It is a single interconnected structure woven together by gravity, time, and matter. But the most mind-bending discovery came when scientists began comparing the cosmic web to other natural systems. When you overlay the structure of the cosmic web with the structure of neurons in the human brain, the similarity is staggering. They share the same mathematical patterns, the same distribution of nodes and links, the same scaling laws, the same ratios of connections. It is as if nature reuses its designs on every scale, from the microscopic to the cosmic. Some physicists suggest this might be a sign of deep underlying principles governing the organization of matter in the universe, that the same rules that govern life might govern the cosmos. But the cosmic web also raises profound questions. Why does the universe have this structure? Why does matter arrange itself into filaments and voids instead of spreading evenly? Why is the web so similar to biological systems? Why does the universe behave as if it is optimizing something? Flow, stability, energy distribution. Some speculate that the cosmic web is the simplest structure that gravity can form on large scales. Others propose that dark matter interactions create a fractal hierarchy. And some thinkers explore more radical possibilities, that the universe is computational, that it updates like a vast program, that the web is the architecture of cosmic information flow. Even more astonishing, recent studies suggest that the cosmic web might influence galaxy behavior in ways we do not yet understand. Galaxies oriented along filaments tend to spin in certain directions. Their shapes correlate with their position in the web. Their growth depends on the angle at which gas flows along filaments. This means galaxies are not isolated objects with random histories. They are shaped by the large-scale structure surrounding them. A galaxy is not simply a collection of stars. It is the expression of the cosmic web at a particular point in space. And yet, despite its immensity, we have only seen a fraction of the web. Most of it is dark matter. Some of it is gas so faint we can barely detect it. The visible galaxies are the ornaments, the decorations, the luminous clues that hint at a much deeper structure. The web is mostly invisible, detectable only through gravitational lensing and cosmic microwave background distortions. It is a hidden world that shapes the visible universe without ever revealing itself directly. Perhaps the most mind-bending idea of all is that the cosmic web might not be unique to our universe. If the multiverse exists, other universes might have their own cosmic webs, their own patterns of structure formation, their own architectures of matter and gravity. And if the geometry of space varies from universe to universe, the webs might look entirely different, stranger, denser, sparser, or built from physics we cannot imagine. The cosmic web is more than a discovery. It is a revelation that the universe is structured, connected, and alive with hidden patterns. A revelation that the cosmos is not random but organized by deep principles we are only beginning to glimpse. A revelation that the visible world is only a shadow of the true architecture of reality. And once you understand the cosmic web, you can never see the universe the same way again. Every star becomes part of a thread. Every galaxy becomes part of a filament. Every cosmic structure becomes part of a much larger whole. You realize you are not living in a disconnected abyss, but inside the vast skeleton of existence. From the time humans first lifted their eyes to the sky, we wondered whether the universe has an edge, whether there is a boundary, a wall, a final frontier where existence ends and nothingness begins. Ancient myths imagined crystal spheres, domes, heavenly shells. Later thinkers imagined infinity. Others imagined a finite cosmic ocean surrounded by the void. But all of these ideas were attempts to answer one haunting question: what lies beyond what we can see? When modern astronomy revealed that the universe was far larger than the Milky Way, that countless galaxies dotted the cosmos like islands in a vast darkness, the question grew louder. And when we discovered that the universe is expanding, swelling, stretching, rushing outward at increasing speed, we realized something even more strange. There is an edge, but not the kind we thought, not a physical boundary, not a cosmic wall. Instead, there is a limit to what we can see, hear, or ever detect. A horizon, a frontier created not by matter but by time itself. A boundary defined by the speed of light and the age of the cosmos. This is the edge of the observable universe, and beyond it lies a realm so mysterious, so unreachable, so profoundly unknowable that it reshapes everything we think we understand about reality. The observable universe is simply the region from which light has had time to reach us since the birth of the cosmos. Light travels at a finite speed. The universe has a finite age. Combine these two facts, and you get a cosmic bubble around us. A sphere centered on Earth, not because we are special, but because we are the observers. This sphere is not the whole universe. It is simply the part we can see. Beyond it, galaxies may exist, stars may shine, matter may form structures more immense than anything in our cosmic neighborhood. But their light has not yet arrived, and may never arrive. They lie beyond our cosmic horizon, and this horizon is not static. It grows. As time passes, light from more distant regions reaches us. The observable universe expands, not because the universe itself waits, but because the universe ages. In the present era, the edge of the observable universe is so far away that the distance bends the mind. Yet the universe itself is even larger, possibly infinite. And the most unsettling truth is this: the part we can see is only a tiny fraction of what exists. Like someone standing in a foggy valley surrounded by walls of mist, we mistake our limited view for the whole landscape. But the universe extends far beyond the fog. To understand how mind-bending this really is, consider this: the observable universe is not defined by where the universe ends. It is defined by where our vision ends. We cannot see beyond our cosmic horizon because light from those regions has not reached us. But there is another layer of mystery. Even if light somehow started its journey toward us now, it could never catch up, because space itself expands faster than the light can travel. Many regions of the universe are receding from us faster than the speed of light, not because they break physics, but because the fabric of space stretches between us at that rate. The expansion of space is not bound by the speed limit of light. The speed limit applies only to motion through space, not to the growth of space. This creates a catalog of zones in the cosmos. Some regions are visible now, some will be visible later, some once were visible but no longer are, because their light has been stretched into invisibility. And some will never be visible at all. There are galaxies whose light left billions of years ago but will never reach us because expansion outpaces their escape signals. They lie beyond a point known as the cosmic event horizon. They exist, they shine, but they are part of a forever unreachable realm. The idea that most of the universe is forever closed to us is profoundly humbling. It means we are trapped in a cosmic bubble, surrounded by a growing darkness. Yet that darkness is not empty. It contains galaxies, stars, planets, maybe even civilizations, all drifting away into cosmic isolation. What lies beyond the observable universe remains one of the greatest unknowns in all of science. Our theories offer glimpses, possibilities, hints, and shadows, but none can tell us for certain. One possibility is that the universe continues infinitely, stretching without end in all directions. This is the simplest idea, that space has no boundary, no edge, no limit. If this is true, the universe we see is merely a tiny drop in an endless ocean. Another possibility is that the universe is finite but unbounded, like the surface of a sphere. You could travel forever without encountering a wall, but space would eventually curve back on itself. In this scenario, the cosmos has shape, it has geometry, it has curvature, but it has no outer boundary. Still, other ideas propose more exotic possibilities, that the universe could be shaped like a torus, like a higher dimensional hypersphere, or like a manifold beyond our comprehension. The strangest possibility is that the universe beyond our horizon might look nothing like the part we inhabit. The laws of physics as we know them may not apply everywhere. They may change across vast scales. Cosmological inflation, the rapid expansion that occurred in the earliest moments after the Big Bang, could have stretched space so unevenly that different regions of the universe became effectively isolated, each with slightly different properties. This leads naturally to the idea of a multiverse, a larger cosmic structure in which our observable universe is one bubble among countless others. In this view, the universe beyond our horizon is not just more of the same. It is a frontier of unimaginable diversity, endless cosmic bubbles, each with different physical constants, different structures, different histories. If this is true, then what lies beyond the observable universe is not merely unknown. It is unknowable in principle. We inhabit one pocket of a far greater whole, and our pocket is only one variation among infinite possibilities. But even without invoking the multiverse, the region beyond our horizon is profoundly mysterious. It may contain superclusters larger than any we can see. It may contain structures spanning hundreds of millions of light years. It may contain cosmic voids as vast as deserts, or it may be uniform and calm. The truth is, we do not know because we cannot know directly. We can infer, we can simulate, we can predict, but we cannot observe. We are staring at a map with the edges torn off. One of the most haunting implications of cosmic horizons is their effect on the fate of the universe. As space continues to expand at an accelerating rate, more and more of the universe slips beyond our ability to observe. Over unfathomable stretches of time, only the nearest galaxies will remain visible. Everything else will fade beyond the horizon. The cosmic web will dissolve into isolated islands of stars surrounded by eternal blackness. The universe will become fragmented, not by destruction, but by expansion. What lies beyond the observable universe will eventually become a realm we once glimpsed but can never see again. This loss of the cosmos is not dramatic. It is silent, slow, inevitable. Cosmic evaporation not through energy but through separation. Yet the horizon is not only a barrier, it is also a window into the past. When we look into the deep universe, we are looking back in time. The farther we look, the younger the universe becomes. We see galaxies as infants. We see stars forming when the cosmos was young. Beyond a certain distance, we see only the glow of the cosmic microwave background, the faint afterglow of the Big Bang. And beyond that, we see nothing. Not because nothing exists, but because the universe at that time was opaque. Light could not travel freely. The early universe was a veil of plasma, glowing hot and uniform. It was only after space cooled that light began its long journey to us. So when we speak of the edge of the observable universe, we are really speaking of a time limit as much as a distance limit. We are peering as far back as light can show us. Beyond that lies a realm before transparency, a time before time as we know it, a cosmic ocean hidden by the opacity of the early universe. One of the most astonishing revelations of modern cosmology is that the observable universe is not even shaped like it appears. Because space expands, objects we see at the edge of visibility are far farther away today than they appear from their ancient light. The light we see left them billions of years ago. But those objects have since drifted to distances far greater than what their light suggests. We see them as they were, not as they are. The cosmos is a hall of mirrors filled with time-delayed images. This fact alone reshapes our intuition. When we look at distant galaxies, we see ghosts, cosmic fossils, light that has traveled nearly the entire age of the universe. What lies beyond our horizon may already be gone, transformed, or displaced, or it might be filled with things we cannot imagine. Perhaps the most profound truth is this: the universe beyond our observable boundary is likely far stranger than anything within it, because the observable universe is biased. It contains only the regions where light has had time to travel. But the universe itself might contain regions shaped by physics untouched by human observation. And yet, despite the mystery, despite the unknowable vastness, despite the horizon that hides more than it reveals, something beautiful emerges from this truth. The edge of the observable universe is not a limitation. It is a challenge. It invites us to imagine. It forces us to dream. It reminds us that existence is bigger than knowledge, that reality stretches beyond comprehension, that we live inside a story whose full narrative lies far outside our field of view. The edge of the observable universe is not the end of the universe. It is the beginning of wonder. Across the vast expanse of the universe, there exist particles so strange, so elusive, so disobedient to the laws of physics as we understand them, that they force us to question whether we truly know what the universe is made of. They slip through matter as if it does not exist. They pass through stars, planets, metal, oceans, mountains, even the atoms of your own body, without slowing, without scattering, without leaving a trace. They are everywhere, all the time, in numbers so enormous that they dwarf every other form of matter, yet you will never see one, never touch one, never feel one. They are called neutrinos, but they are only the beginning. Because beyond neutrinos lies a deeper realm of mystery. Hypothetical particles such as axions, sterile neutrinos, and entire classes of unknown entities that may fill the universe like invisible fog. These particles do not simply challenge physics, they rewrite it. To understand why these particles are so mind-bending, You have to imagine the early universe, moments after the Big Bang, when temperatures were so incredibly high that matter could not exist in any familiar form. The universe was a sea of energy, particles flickering into existence and vanishing in an instant. As space expanded and cooled, most particles combined or decayed, leaving behind the familiar building blocks of atoms. But some particles, born in that early inferno, remained. They drifted through the cosmos unchanged, silent witnesses to the entire history of the universe. These particles are neutrinos, and they are perhaps the strangest residents of the cosmic zoo. Every second, trillions of neutrinos pass through your body without interacting with a single atom. They come from the sun, from cosmic rays hitting the atmosphere, from supernovae exploding across the universe, and from the Big Bang itself. Neutrinos barely notice matter, and matter barely notices them. They are like cosmic phantoms, passing through everything as if reality were made of smoke. But the most unbelievable thing about neutrinos is that they should not exist as they do. According to the earliest versions of the standard model of particle physics, neutrinos were supposed to have no mass, but experiments later revealed that neutrinos oscillate between different forms as they travel, and this oscillation is only possible if they have mass. This discovery was so shocking that it won the Nobel Prize, but it also broke the standard model. It forced physicists to admit that our most successful theory of matter was incomplete. The universe does not obey our rules. It forces us to rewrite them. And neutrinos, for all their strangeness, may only be the first layer of a deeper mystery. Because the type of neutrinos we know might not be the only ones that exist. For years, scientists have suspected the existence of an even more elusive type of neutrino, a sterile neutrino. Unlike the neutrinos we have detected, which interact through the weak nuclear force, sterile neutrinos would not interact at all except through gravity. They would be nearly impossible to detect. And yet, they might explain one of the greatest puzzles in cosmology: dark matter. If sterile neutrinos exist, they could account for a significant portion of the universe's hidden mass. They could shape galaxies, influence structure, and alter cosmic evolution. But so far, they remain hypothetical, hidden behind layers of mathematical suggestion and experimental hints, like shadows of particles we cannot see. But as strange as sterile neutrinos are, axions are even stranger. The axion was proposed to solve a fundamental problem in particle physics: why the strong nuclear force behaves the way it does, refusing to violate a symmetry it mathematically should. The axion was invented as a fix, a patch, a mathematical trick. But then, something unexpected happened. Physicists realized that axions, if they exist, could also explain dark matter. They would be incredibly light, incredibly numerous, and incredibly weakly interacting, exactly the characteristics needed for dark matter. Axions would form a new kind of matter, not made of particles in the traditional sense, but of a field, a rippling waveform filling space. If axions exist, the universe would be permeated with a subtle vibration, a background hum of invisible mass shaping everything without ever revealing itself. Experiments around the world are now searching for axions, using everything from resonant cavities to magnetic fields, to ultra-sensitive detectors chilled close to absolute zero. But the axion remains hidden, like a cosmic secret waiting to be discovered. The deeper we look, the more obvious it becomes that the matter we know, the protons, neutrons, and electrons that build stars and planets, is only a fraction of what exists. Beneath the surface lies an unseen world of particles that do not behave like anything we understand. Some pass through matter untouched. Some barely interact at all. Some may exist only as vibrations in invisible fields. Some may flicker between realities, popping in and out of existence in ways we cannot yet detect. This realm of unknown particles is not a small detail. It may be the majority of the universe. The standard model, for all its triumphs, only describes a tiny slice of reality. The particles we know are the tip of an iceberg whose true depth lies in the unknown. Even more mind-bending is the possibility that these strange particles might interact with each other in ways we cannot detect. A hidden sector of physics may exist, a dark world of particles, forces, and interactions parallel to our own. In this hidden world, particles may collide, combine, decay, and interact through dark forces completely invisible to the ordinary matter we are built from. Only gravity would reveal their existence, pulling on galaxies, shaping the cosmic web, and influencing the expansion of the universe. Imagine two universes overlapping, one made of familiar particles, one made of dark particles, both occupying the same space but interacting only through gravity. It would mean we live inside a two-layered reality without realizing it. A bright world and a dark world intertwined. But the strangeness does not stop with axions and sterile neutrinos. There may be entire families of exotic particles that solve mysteries we have not yet fully recognized. Dark photons, for example, could be particles that carry forces in the dark sector, analogous to how photons carry electromagnetic force. If dark photons exist, they might allow dark matter to interact with itself, forming structures we cannot see. Then there are hypothetical supersymmetric particles, heavier cousins of known particles that mirror them in a deeper symmetry. Supersymmetry was once considered one of the most elegant theories in physics, potentially explaining dark matter, unifying forces, and solving problems in the Standard Model. But after decades of searching with the Large Hadron Collider, these particles remain hidden. Still, some physicists suspect they may exist at energies just beyond our current reach, waiting for the next generation of colliders to reveal them. The more we explore the realm of unusual particles, the more we realize that the universe is not made of familiar matter with a few oddities sprinkled in. The universe is a cathedral of strange physics, built from components we barely understand. The visible world may be nothing more than a luminous crust floating atop a vast ocean of invisible particles. And here is the most unsettling truth. These strange particles may hold the key to the fate of the universe itself. Dark energy, the mysterious force accelerating cosmic expansion, could be linked to quantum fields associated with unknown particles. The vacuum might not be empty at all, but filled with fluctuating fields whose behavior determines the future of space-time. Tiny particles might influence the destiny of galaxies. The smallest pieces of reality might govern the largest structures in existence. But perhaps the most mind-bending thought of all is this. These particles, so ghost-like and elusive, may be the oldest messengers in the universe. Neutrinos produced in the earliest moments after the Big Bang still drift through space today, untouched and unchanged. They carry information about the universe's first seconds, encoded in their energy and distribution. Detecting them is like listening to an ancient whisper from the dawn of existence. And someday, when we finally decode these whispers, we may discover that the universe is far older, far stranger, and far more filled with unseen matter than we ever dared to believe. The universe is not built from what we see. It is built from what we do not. And the particles we cannot detect, the particles that slip through matter like ghosts, may be the foundation of reality itself. Across the grand canvas of the universe, galaxies drift like glowing islands in an endless ocean of darkness. They spin, collide, merge, and evolve, following the deep currents of gravity that sculpt the cosmos. For a long time, we believed these galaxies moved only because of the matter inside them, their stars, their black holes, their dark matter halos. But as astronomers began to map the movement of galaxies on much larger scales, they found something disturbing, something enormous, something invisible. A force strong enough to pull not just a few galaxies, not just a small cluster, but entire regions of the universe in one direction. A gravitational anomaly so vast and so mysterious that scientists gave it a name that sounds more like something from mythology than astronomy. They called it the Great Attractor. And to this day, we do not fully understand what it is. The story begins with galactic motion. Every galaxy moves through space, not randomly, but influenced by the gravitational pull of nearby structures. The Milky Way and the Andromeda Galaxy are moving toward each other. Galaxy clusters move toward even larger clusters. All of this makes sense. Gravity binds the universe together. But when astronomers measured the motion of hundreds of galaxies around us, they noticed something strange. The galaxies were not only moving because of the visible structures near them, They were being pulled toward a region of space that seemed to contain nothing. A point in the sky in the direction of the constellation Norma, a region hidden behind the dense plane of our own Milky Way, making it difficult to observe. Yet something behind that curtain exerts a gravitational pull so enormous that our entire galaxy is rushing toward it at hundreds of kilometers per second. Imagine standing in a river and noticing that the water around you flows in a particular direction. You assume the riverbed slopes that way, or perhaps there is a waterfall ahead. But instead, you discover something more astonishing. The entire river valley is being pulled toward an unseen force. That is the situation astronomers faced. The Milky Way, the local group of phytogases, galaxies, and the broader Virgo supercluster are all moving toward an unseen gravitational source, a mysterious gravitational sink known as the Great Attractor. What makes this even more mind-bending is that the Great Attractor is not a small object. It is not a black hole. It is not a cluster. It is an entire region of space spanning hundreds of millions of light years, filled with dense matter, both visible and invisible, all tugging on the surrounding cosmic web. But because this region lies behind the Milky Way's thick band of dust and stars, we cannot see it directly in visible light. For decades, it was a gravitational shadow, inferred only from the movement of galaxies. Only when infrared and radio telescopes pierced the galactic plane did we begin to glimpse what lies there. What we found was astonishing. Behind the obscuring dust lies a massive concentration of galaxies known as the Norma cluster, part of a far larger structure called the Norma supercluster. But even this is not the full story. This region is only a piece of an even more colossal structure, the Laniakea supercluster. Laniakea, the structure that contains the Milky Way, is not a traditional cluster. It is a continent of galaxies, hundreds of millions of light years across, all flowing along gravitational rivers toward a single basin, the Great Attractor. It is as if the universe were sculpted into vast watersheds of gravity, and we are sitting in one of the largest. Yet the mystery deepens, because even when we account for the galaxies in the Norma region, the gravitational pull still seems too large. The Great Attractor might be only one part of a larger gravitational system, or it might be connected to something even more powerful farther beyond. Some astronomers propose that the Shapley supercluster, an even more massive structure lying deeper in the same direction, might be influencing galactic motion as well. The Shapley concentration contains thousands of galaxies and may be the true powerhouse behind the pull. If so, the Great Attractor is not a single object, but a gravitational slope created by several interconnected structures. And here is where the story becomes almost unbelievable. When scientists mapped larger and larger cosmic flows, they discovered that galaxies far beyond our region of the universe are also moving in coordinated ways, as if drawn toward a gravitational source even more distant than Shapley. This deeper pull is known as the dipole repeller, or sometimes the dark flow. It implies that the universe's expansion on the largest scales might not be entirely uniform. Somewhere beyond our horizon, beyond what we can observe, lie structures so massive that their gravitational influence reaches across billions of light years. These structures may not even be in the observable universe. They may lie beyond our cosmic horizon, shaping our motion in ways we cannot directly perceive. Think about that for a moment. There may be regions of the universe we will never see that are pulling on us right now. This challenges the most fundamental assumption in cosmology, that the universe is homogeneous on large scales. It suggests the universe may not be the same everywhere, that enormous structures might exist beyond our view, that the cosmic web might stretch far deeper than we ever imagined, that the universe is not just vast, but structured in ways so large that we cannot comprehend them. At this point, the Great Attractor is not just a gravitational anomaly. It is a symbol of the universe's hidden architecture, a reminder that even with all our telescopes, all our maps, all our theories, the majority of the cosmos remains unseen. But what makes the Great Attractor even more bewildering is the possibility that it may not be a gravitational pull at all, at least not solely. Some theories propose that the flow of galaxies might be influenced by the shape of space-time itself. Large-scale curvature could create apparent motion toward certain regions. The geometry of the universe might funnel matter in specific directions. Alternatively, dark matter filaments may be thicker in this region, creating unseen gravitational pathways that guide galaxy movement. If the cosmic web is deeper and more complex than we think, the Great Attractor could be a knot where multiple massive filaments intersect. In this view, galaxies are not drifting randomly. They are sliding along invisible gravitational highways woven from dark matter. And the Great Attractor might be the single largest crossroads in our cosmic neighborhood. Yet another possibility is even more radical. What if the flow we observe is partly an illusion created by the way we measure cosmic expansion? If the expansion rate of the universe varies slightly in different directions, something that could happen if the universe contains large-scale anisotropies, then apparent motion toward a region might not be caused by gravity at all. It might be caused by variations in the cosmic expansion fabric. The idea that the universe might expand at slightly different rates in different regions is profoundly disruptive. It suggests the universe may not be symmetrical on the largest scales. It challenges the cosmological principle that the universe is uniform when viewed at large distances. And if proven true, it would force a rewrite of cosmology from the ground up. But there is another, even more unsettling theory. Some physicists propose that the Great Attractor might not be a structure within our universe, but an effect caused by another universe. If the multiverse exists, universes could interact gravitationally through higher dimensions. The Great Attractor could be a gravitational shadow cast by a structure in a neighboring universe. This idea is speculative, but it highlights the profound mystery surrounding the Great Attractor. And yet, despite its enormous pull, the Great Attractor is not a threat. We are not falling into it in any catastrophic sense. Our motion toward it is simply part of the grand dance of galaxies across the cosmic web. But the fact that we are moving toward something we cannot fully see or understand is humbling. It reminds us that our place in the universe is not fixed. The Milky Way is not static. It is drifting, flowing, part of a cosmic river drawn toward a gravitational basin whose full nature remains hidden. Perhaps the most profound truth is this: the universe is not only expanding, it is flowing. Galaxies move along currents invisible to us. Structures billions of light years wide shape the motion of entire cosmic regions. Gravity weaves rivers and valleys across the universe, and we are drifting through one of them without fully knowing why or where it leads. The Great Attractor, whatever it truly is, reveals the universe as a place far more structured, far more interconnected, far more dynamic than we ever imagined. It reminds us that the cosmos does not merely sit in space. It moves, it drifts, it responds to forces larger than galaxies, larger than clusters, larger than superclusters, forces that span unimaginable distances. And we are part of that motion, carried along by the deep currents of the cosmic ocean. Time is the most familiar thing in your life, yet the least understood. You feel it flowing, you measure it, you chase it, you lose it, you regret it, you try to save it, you watch it slip from your hands like sand through your fingers. But time is not what you think it is. It never was. The universe does not experience time the way you do. Time is not an absolute rhythm beating outside the universe. It is not a universal clock ticking the same for every observer. Time is woven into the fabric of space itself. It bends, it stretches, it slows, it warps, it changes depending on where you are, how fast you move, and how gravity shapes the world around you. The deeper you look into the cosmos, the more obvious it becomes that time is not a constant. It is an illusion shaped by motion, mass, and the structure of space-time. And once you understand this, you begin to realize that the universe may not have a single timeline at all. It may have countless timelines, flowing at different rates, overlapping and diverging in ways that defy intuition. To grasp the strange truth about time, imagine two clocks. One rests on the surface of the Earth, the other floats high above the planet, where gravity is weaker. These two clocks, identical in every way, will not tick at the same pace. The clock on Earth will tick slightly slower. The difference is tiny, measurable only with extremely precise instruments. But the fact remains, gravity slows time. This was one of the first predictions of relativity, and when scientists measured it, the universe confirmed it. Time is not a universal rhythm. It is influenced by gravity, shaped by mass, warped by the curvature of space-time. The same is true for motion. As an object moves faster, time slows down for it relative to a stationary observer. If you could travel near the speed of light, time would stretch like taffy. Minutes for you might be hours for others. Hours for you might be years for the people you left behind. This is not science fiction. This is not theory. This is reality. It has been proven by high-speed particle experiments, by precise atomic clocks on airplanes, by countless measurements across decades. The faster you move, the slower time becomes. This means time is not something the universe experiences universally. It is something each observer experiences personally. Your time is not my time. Your time is not a galaxy's time. Your time is not the universe's time. Every motion, every gravitational well, every curvature of space creates its own unique flow of time. But the implications go deeper, far deeper, than simple differences in clocks. Because if time can bend and stretch, if it can slow and warp, then the way events unfold is not absolute. The sequence of events is not the same for all observers. In some situations, two observers may disagree on the order in which events happen, and both will be correct in their own frame of reference. That is how flexible time really is. There is no universal now, no single moment that the entire universe shares. When you look at the night sky, you see stars as they were long ago. Some are hundreds of years behind, some thousands, some millions. Entire galaxies appear as they existed billions of years before you were born. This alone is strange enough. But there is a deeper twist. Those galaxies, based on relativity, experience time differently than you do. Their clocks tick differently because their gravity, their motion, and their cosmic environment differ from yours. When you look at a distant galaxy, you are not just looking back in time. You are looking across a different time rate altogether. And then there is the most extreme demonstration of time's distortion, the black hole. Near a black hole, gravity becomes so intense that time slows dramatically. The closer you get to the event horizon, the slower time becomes. For an outside observer watching someone fall toward a black hole, the falling person appears to move slower and slower, as if frozen in time at the edge. But from the perspective of the person falling, nothing unusual happens. They cross the horizon without noticing anything special. Their time flows normally. But for the outside world, they are frozen forever. A single event can hold two completely different realities, both true. This is the madness and beauty of time. If time can stretch, warp, and break apart like this, then what does it even mean for two moments to be connected? What does it mean to say something happened before something else? In the universe, before and after depend entirely on where you are and how you move. There is no cosmic master timeline guiding everything. Time is local, not universal. This leads to a wild but true idea. The universe does not evolve through time. The universe contains time. Space-time is a four-dimensional structure, and all moments, past, present, and future, exist within it. Your experience of time flowing is not the universe changing. It is your consciousness moving along one path through a timeless fabric. The universe does not flow. You do. This view, sometimes called the block universe, suggests something profound. The future may already exist. Every moment is a location in space-time, already part of the cosmic tapestry. You are simply traveling through it, experiencing each moment one by one. But the structure exists independent of your passage. This idea is unsettling because it challenges your sense of free will, your belief in choice, your belief in change. but relativity points strongly in this direction. Time is geometry, not motion. Yet the block universe is not the only interpretation. Quantum physics introduces uncertainty, randomness, and probabilities. According to quantum theory, the future does not exist until it happens. Possibilities collapse into reality only when observed. The universe, in this view, is not a fixed block but a branching tree of potential outcomes. Time is not a frozen dimension but a dynamic wave function. Reality does not pre-exist, it emerges, and the observer plays a role in shaping it. These two views, the block universe of relativity and the evolving universe of quantum mechanics, coexist uneasily, pointing to a deeper truth we do not yet understand. Time may not be a single phenomenon. It may have multiple layers, some deterministic, some probabilistic, some geometric, some emergent. The universe may have one kind of time for gravity and another kind for quantum events. We simply do not know. Even stranger still is the possibility that time itself may not be fundamental. It may be emergent, something that arises only when many particles interact in complex ways. In some theories, the universe at the smallest scale has no time at all. Time emerges the way temperature emerges from molecules, or the way sound emerges from vibrations. At the quantum level, time might not exist. It may be an illusion woven by our brains as they interpret physical processes. If time is not fundamental, then the universe may be timeless at its core. All of existence might be a web of relationships rather than a sequence of events. What we call a moment may simply be a pattern in that web. This raises one of the most profound questions of all. If the universe does not experience time the way we do, then what does it mean for the universe to have a beginning? What does it mean for it to have an end? If time is emergent, then the Big Bang may not be a beginning in the way we imagine. It may simply be a boundary of our understanding, a point beyond which time loses meaning. Likewise, the end of the universe, whether heat death, collapse, or transition, may not be an ending at all, but a transition into a state where time dissolves. There are physicists who propose that time may reverse in certain regions or under certain conditions. If you alter entropy, gravity, or quantum structure enough, the arrow of time might flip. In a collapsing universe, time might run backward relative to our experience. In certain quantum phenomena, time symmetry is nearly perfect. The universe might not care which direction time flows. Some theories suggest that time flowed differently during different epochs of cosmic history. The early universe may have had a different time rate than the modern universe. Some theories even propose that the speed of light changed early in cosmic history, which would alter time's structure entirely. The idea that time may not always behave the same way is eerie. It means the universe might pass through eras with different temporal laws. It means time is not a fundamental property, but a fluid one. Then there is the question of consciousness. Why do we experience time as a flow at all? Why do we perceive a past and anticipate a future? Why does time feel directional, even though many physical laws do not require a direction? This is the deepest question of all. Time may exist because consciousness exists. The feeling of flow might be something the brain creates as it stitches together states of awareness. In this view, time is not something the universe generates. It is something the mind generates as it moves through the universe. Neuroscientists have found that the brain does not sense time directly. It constructs it. It infers it. Time perception depends on attention, memory, emotion, and experience. When you are scared, time stretches. When you are bored, time slows. When you are focused, time disappears. Time is not a universal experience. It is a psychological construct layered on top of physical processes. If consciousness shapes the experience of time, then each observer inhabits a slightly different temporal reality. Your time is unique to you. Your now is not the universe's now. And perhaps in some profound way, your perception of time creates your version of the universe. The strangest thought is that time might not be a fundamental truth, but a useful illusion that helps conscious beings navigate reality. Nature may not need time. Only minds do. As you move deeper into the universe, time becomes stranger, slower, faster, warped, twisted, fragmented, or possibly non-existent. It may be nothing more than a tool the mind uses to interpret the unfolding of events. Or it may be a geometric property of space. Or it may be an emergent phenomenon. Or it may be a shadow cast by something deeper and more fundamental that we have not yet discovered. Whatever the truth may be, one thing is certain: time is not what you think it is. It never was. And the universe is far more mysterious, far more fluid, and far more complex than any simple ticking clock could ever describe. Across the silent darkness of the cosmos, there are moments when the universe seems to speak, not with words, not with light, but with sudden pulses of energy that erupt from the deep void and vanish before we can even understand what happened. Signals that defy explanation, bursts that carry more power than entire galaxies, flickers that last for less than the blink of an eye. For decades, astronomers have pointed their instruments toward the night sky, expecting to find silence. Instead, they found something that feels suspiciously like messages, messages not necessarily from intelligence, but from the universe itself. Mysterious flashes, strange repeating patterns, unusual radio bursts, cosmic whispers that do not fit neatly into our understanding of physics. And every time we discover one of these signals, we must confront the possibility that the universe is far stranger than we imagined, and that we are not the only observers in the cosmic dark. One of the most mind-bending discoveries of recent decades is something called a fast radio burst. These bursts are unimaginably powerful eruptions of energy that last only a fraction of a second. In that tiny sliver of time, a single burst can release as much energy as the sun emits in an entire century. That alone is astonishing. But what makes these bursts even more mysterious is their source. They come from distant galaxies billions of light years away. They appear out of nowhere. They do not repeat, except for the ones that do. They follow no known pattern, except for the few that seem to have patterns. They should be rare, except that they happen constantly all across the sky. When the first fast radio burst was discovered, scientists assumed it was an error, a glitch, maybe interference from Earth. But then another was found, and another, and another. The more astronomers looked, the more they realized these things were everywhere. They are among the most powerful and mysterious phenomena in the universe, but their origins remain unknown. Some theories propose that fast radio bursts come from magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's. These objects can crack and quake, releasing titanic flares that travel across the cosmos. Others suggest black holes might be involved, perhaps interacting with neutron stars or swallowing matter in ways we do not yet understand. Some suggest collisions between exotic objects we have not yet detected. And then there are the bold theories, the ones that suggest that fast radio bursts might be techno-signatures, artificial signals created by advanced civilizations using massive energy beams for propulsion or communication. It is tempting to jump to dramatic conclusions. A burst that powerful, that precise, that sudden, feels almost engineered. But science demands caution. We cannot assume intelligence where nature might suffice. Still, the fact remains. These signals are unlike anything we expected to find. They defy conventional astrophysics. And the few that repeat, sometimes in cycles, sometimes at random, make the mystery even deeper. But fast radio bursts are only one type of unusual cosmic signal. Another is the enigmatic wow signal detected in the 1970s. A single narrow band signal that lasted for more than 1 minute. It came from deep space. It matched no known human transmission. It was sharp, clean, and highly unusual. When astronomer Jerry Amon saw the data, he wrote the word "wow" next to it, and the name stuck. To this day, no one has ever explained the wow signal. It was never detected again. It came and went, leaving behind a question that lingers in our collective imagination. Was it natural? Was it artificial? Was it a coincidence? Or was it the one moment in human history when the universe whispered something directly at us? For decades, scientists searched the same region of the sky for another signal like it, but the silence was absolute. The WOW signal remains the most tantalizing single data point in the search for extraterrestrial intelligence. It does not prove anything. It does not solve anything. But it reminds us that the universe is vast, complex, and full of surprises. Then there are the repeating signals that carry structure, not language, not content, but patterns. Some fast radio bursts repeat in cycles that appear almost too regular to be random. One such burst seems to follow a pattern, active for a while, then silent for a while, then active again. Nature can produce cycles, of course. Stars can pulse, magnetars can flare, black holes can interact. But each time we find a repeating structured signal, we are reminded that the universe might hold more than chaotic noise. It might hold rhythms. Some cosmic signals come from the early universe. These are not messages from intelligence, but relics from the dawn of time, faint whispers of the Big Bang imprinted in the cosmic microwave background. These ancient signals reveal the earliest structure of the universe, but they also contain anomalies, cold spots, and unexplained patterns that hint at something deeper. These strange irregularities may come from quantum fluctuations, or they may come from something else, collisions between bubble universes, imprints of cosmic defects, or interactions with forms of matter we have not yet discovered. At the opposite end of cosmic time, we detect signals from the deaths of stars. Gamma-ray bursts among the most violent events in the universe send beams of energy sweeping across space. These bursts can sterilize entire galaxies. They are so intense that if one occurred within a few thousand light-years of Earth, life on this planet might be wiped out instantly. Yet we only detect their echoes across billions of light-years. These events are natural, but their scale makes them feel almost intentional, like cosmic alarms marking the most extreme transformations of matter. Another class of signals comes from gravitational waves. These waves are ripples in the fabric of space-time itself, created when massive objects collide, black holes merging, neutron stars smashing together. These events shake the universe, sending distortions across space at the speed of light. When the first gravitational wave was detected in the 21st century, it was a moment that changed physics forever. Suddenly, we were listening to the universe in a new way, not through light, not through particles, but through the movement of space-time itself. Gravitational waves reveal events that cannot be seen with ordinary telescopes. They open a new sense, a cosmic hearing, allowing us to detect collisions billions of light-years away. And some gravitational wave patterns are unexpected. Some are too loud, some seem too frequent. Some may come from objects we do not yet understand, perhaps primordial black holes formed in the earliest moments after the Big Bang, or perhaps something even stranger. The more we listen, the more the universe surprises us. There are also radio emissions that appear to come from the center of the Milky Way. Strange pulses, sudden bursts, signals that turn on and off in ways that defy the behavior of known stars. Some appear only once and never repeat. Others appear for weeks and vanish. Some brighten and dim with patterns that no known object produces. These may be magnetars, or they may be something entirely new, a class of cosmic object we have not yet discovered. Every time astronomers think they understand the sky, a new signal appears that forces us to rethink everything. But the possibility that haunts the imagination is the idea that some of these signals might be artificial. Not because we assume aliens, not because we want them, but because the universe is old, unimaginably old, and intelligence may not be rare. If technological civilizations arise, survive, and evolve, they might create signals powerful enough to cross galaxies. They might use radio beams to accelerate spacecraft. They might use directed energy for communication. They might produce bursts that look natural unless you know what you are looking for. The truth is, we do not know. We cannot know yet. But the possibility remains. Some scientists suggest that if alien civilizations exist, their signals would not be obvious. They might be embedded in fast radio bursts. They might be hidden in narrow band frequencies. They might be encoded in structures we have not yet learned to decode. Or they might use methods we cannot detect at all, quantum signals, neutrino communication, or gravitational encoding. The universe is vast enough for countless possibilities, but even without intelligent sources, the signals we detect reveal a universe filled with phenomena more extreme than any imagination. They show us that the cosmos is not quiet. It is alive with activity, explosions, pulses, whispers, flashes, waves. It is a universe constantly communicating, not intentionally, but naturally, through the violent and mysterious processes that shape matter and energy. Perhaps the most haunting question is this: how many signals have we not detected? How many bursts happened while no telescope was pointed in the right direction? How many whispers passed through us before we had the technology to listen? How many messages, natural or artificial, did we miss because we were not ready? We are infants in a galaxy billions of years old. Our technology is young, our listening window is small, our attention is limited. The universe may have spoken countless times before we were here, and it will continue speaking long after we are gone. What we detect today is only the beginning. A tiny fraction of the cosmic conversations happening all around us. We are learning to listen. We are learning to see not just with our eyes, but with radio telescopes, gravitational detectors, neutrino observatories. Every new instrument opens a new sense. Every new sense reveals a universe richer and stranger than we expected. And as we sharpen our tools and deepen our reach, we may find signals that challenge not just our science, but our place in the universe. Signals that reveal new physics, signals that point to exotic objects, signals that hint at other forms of life, signals that reshape our understanding of reality. The universe is not silent. It never was. We are only now learning how to hear its voice. For as long as humanity has existed, we have searched for meaning in the sky. We have looked upward, wondering what lies beyond the stars, beyond the swirling galaxies, beyond the edge of everything we know. We have mapped the heavens, charted the motions of planets, traced the faint glow of ancient starlight, traveling across unimaginable distances. Yet, every time we peel back one layer of the cosmic mystery, we find not clarity, but deeper shadows. We discover truths that upend our assumptions, forces that bend the laws we thought were unbreakable, particles that refuse to behave, signals that defy interpretation, and structures so massive they reshape our understanding of scale itself. The universe is not a solved puzzle. It is a living enigma, constantly revealing new faces, new depths, new contradictions. And perhaps the greatest mystery of all is this: the more we learn, the stranger everything becomes. Standing under the night sky, it is easy to imagine the universe as a vast, silent backdrop. But through all the discoveries we have explored, dark matter pulling on galaxies like invisible hands, dark energy pushing space apart faster and faster, black holes twisting reality into impossible geometries, neutrinos slipping through everything like ghosts, cosmic signals erupting with the energy of 100 billion stars, one thing becomes undeniable. The universe is not silent, it is not static, it is not simple. It is a storm of forces, a symphony of energy, a sea of particles and fields interacting in ways we barely understand. We once believed the universe was composed of things we could see: stars, planets, gas, dust. But now we know that the visible world is only a thin surface layer floating atop a deeper ocean of hidden structure. Most of the matter in the universe is invisible. Most of the energy is mysterious. Space itself stretches and curves with a will of its own. The familiar world you inhabit, the world of atoms, molecules, and light, is only a small fraction of reality. A cosmic island surrounded by a vast darkness we cannot yet map. Yet even the darkness is alive with structure. Galaxies form cosmic filaments that stretch across unimaginable distances, weaving a network that resembles the neural pathways of a cosmic mind. Gravity sculpts the universe into patterns that repeat across scales, from the clustering of galaxies to the rippling of matter in the early universe to the swirl of gas around a supermassive black hole. The universe is fractal in nature, Patterns echo through time and space. The large resembles the small. Chaos contains order, and order contains chaos. And through it all runs time, not the simple ticking clock of human experience, but a fluid, malleable dimension that warps near massive objects, stretches in vast cosmic voids, and dissolves at the edges of black hole horizons. Time is not universal. It is not equal. It is as alive and dynamic as space itself. Your experience of time is only one version among countless others scattered across the cosmos. The more we study the universe, the more we realize how limited our senses are. We evolved to survive on a small blue planet orbiting a single star. Our eyes detect only a tiny sliver of the electromagnetic spectrum. Our ears hear nothing of the cosmic symphony. Our skin feels only the faintest whisper of radiation constantly passing through us. Most of the universe flows around us unnoticed. We live inside a reality we perceive mostly through inference, mathematics, and instruments that extend our senses far beyond what evolution gave us. But even with all our tools, telescopes, detectors, observatories, we still face horizons we cannot cross, limits we cannot bypass. The speed of light restricts what we can see. The age of the universe restricts what information has had time to reach us. The expansion of space pushes galaxies beyond visibility. The cosmic horizon hides vast regions forever. We live inside a bubble of observability, an island of light surrounded by an ocean of darkness stretching far beyond our reach. And yet, this limit is not a barrier to curiosity. It is the very reason curiosity exists. The unknown fuels imagination. The unseen drives exploration. Every mystery we encounter, every strange particle, every exotic signal, every gravitational anomaly is an invitation to push deeper into the cosmos. The universe does not reveal itself all at once. It reveals itself through riddles, clues, contradictions, and moments of revelation. Consider how far we have come. Humanity once believed Earth was the center of everything. Then we discovered the sun was a star among countless others. Then we discovered the Milky Way was one galaxy among innumerable galaxies. Then we discovered the universe was expanding. Then we discovered it was accelerating. Then we discovered dark matter, dark energy, the cosmic microwave background, gravitational waves, and fast radio bursts. Each discovery shattered an old certainty and replaced it with a deeper mystery. This is the great cosmic paradox. The more answers we find, the more questions arise. And the biggest question of all remains unanswered. Why does the universe exist in the first place? Why does anything exist? Why is there something instead of nothing? Some theories suggest the universe emerged from a quantum fluctuation. Others propose that the universe is a bubble in a multiverse, one of infinitely many cosmic regions, each with its own laws of physics. Others imagine that the universe cycles endlessly through births and deaths, collapsing and re-expanding in an eternal rhythm. Some believe time itself may be an illusion, and that the universe is not something that exists in time, but something that contains all time at once. There is even the possibility that consciousness plays a role, not in creating the universe, but in interpreting it, shaping the way we perceive time, space, and reality itself. Our minds may not merely observe the universe, but participate in it by collapsing probabilities into events, by giving structure to perception, by defining the flow of time through awareness. The universe might be a dialogue between physical law and conscious observation, an interplay between matter and mind. But these ideas remain speculative, beautiful, haunting, unresolved. The truth is that the universe hides more than it reveals, and yet every hidden truth draws us closer. What makes the cosmos even more astonishing is that we, tiny beings made of stardust, have the capacity to understand it at all. Our atoms were forged in ancient stars. Our elements were born in supernovae. The iron in your blood came from the death of a star. The calcium in your bones came from exploding suns. Every breath you take is connected to the universe's oldest events. You are not separate from the cosmos. You are a piece of it that has become aware. In a sense, When we study the universe is studying itself. Through your eyes, through your mind, reality becomes conscious of its own structure. Through curiosity, the cosmos awakens. This is why science is not just knowledge, it is participation, exploration, a cosmic awakening. The universe will continue to surprise us. We will find new particles that break our theories. We will detect new signals that challenge our understanding. We will uncover new structures that make the Great Attractor feel small. We will peer deeper into space-time through gravitational waves. We will map the cosmic web in greater detail. We will study black holes the way earlier generations studied eclipses. We will listen to the universe with instruments that do not yet exist. And somewhere, out there in the darkness, lies a discovery so shocking, so profound, so paradigm-shifting that it will rewrite everything we believe about existence. Every era of science has such a moment. We have not had ours yet. The universe is not what we think. It is not what we imagine. It is not what we expect. It is more, always more mysterious, more chaotic, more elegant, more terrifying, more beautiful. And as long as we continue to look upward, to wonder, to question, the universe will continue to reveal itself, layer by layer, puzzle by puzzle, mystery by mystery. In the end, the greatest secret of the universe may be this. The search for understanding is endless because the universe itself is endless, not just in size, but in depth, in possibility, in meaning. And that search, that hunger to know what lies beyond the next horizon, is what makes us human. It is what makes our brief existence meaningful. It is what turns a small species on a pale blue dot into explorers of infinity.